Okay, so I'm more audible. So let's me start from beginning. Okay, so yesterday we discussed MOSFET. So MOS. So I'll just briefly discuss what is MOSFET. So basically, we are talking about transistor. First of all, we should know that we are talking about controlling device. We are trying to control the flow of charge. So we are talking about transistors. T field of transistor. First of all, what is transistor? We discussed T for transistor is like a pipe. Something there's a water flow. There is a water flow, and we are having a pipe to control the water flow. And we can turn the pipe left or right, anti-clockwise or clockwise. So net effect, the water flow is controlled through the pipe, right? It can increase or decrease, like pressure increasing. This is water flow. This is the tapping or changing, switching, or the pressure you're applying on the tap. Okay, it's changing the water flow. It may be increasing or it can be decreasing, whatever. But ultimately, there is some control based on the pressure applied on the tap or the pipe or the switching clockwise and anti-clockwise. There is a change in the water flow. So this is analogous to the analogous to the transistor, right? So we are ultimately interested in controlling the electron flow. So in transistor, what happened? The same thing will be coming like this. So this is the controlling. This is a current. This is instead of water, we have current. And what is the tank? The water is coming from some tank, right? So some tank where water is kept, right? So this is analogous to the voltage source, right? Whose height I can vary. Voltage source height I can vary. So the pressure of water increases. So here also I can increase the pressure on voltage, right? So this tapping mechanism, this controlling mechanism of the tap is actually so kind of voltage or current in a transistor also, which we can vary, right? So here also I'll get a curve versus current versus the controlling voltage or VG or whatever. So here it is in a MOSFET. This is a gate. This is source, drain. So this can be gate source voltage. So I'm giving a voltage across this point and the ground, that is source. Source is ground. So VGS. VGS is my controlling voltage. So I'll get a current something like this in MOSFET or something, or not exactly like this. Maybe more steeper. Okay, not exactly like this, or it can be more linear or something. Okay, or it can be reverse also. Ultimately, this is a control. We are trying to control the current based on the voltage. So MOSFET, we discussed what is MOSFET. So we are controlling. There's a silicon N-type material, for example. On this N-type material, will go to P-type material after proper process, and over this we'll give a semiconductor. We'll add a semiconductor materials, and then we have metal here, and then we connect this to voltage. So this is metal, oxide, and semiconductor, right? Ultimately, we are doing field effect transistor. So metal oxide semiconductor FET, field effect transistor we have. So this is called gate, and this is called drain or source or reverse. It's called source, right? So what is the principle? In N channel, there's a lot of electrons all over the material. So initially, this is not conducting because there's a P channel, N channel, P channel. So this is not conducting. There's even if you apply voltage or push some current, there's no current, right? There is no flow, uh, you know, flow of current. So what we need to increase the conductivity or decrease the resistivity. So I'll give a voltage here, plus voltage. I give a plus voltage here, VG or VGS. Here also this is based on gates, so VGS. I call VGS with respect to ground source, right? So this is also VGS. So I give a voltage VGS. So that means this positive voltage. So it attracts. First of all, it repels all. So first of all, it repels. Okay, this is N channel, so I should give a negative voltage here. So if I give a positive voltage, what happens? All these electrons will accumulate on the top layer, and there will not be conduction. Resistance will increase on, there will not conduction. But if I apply a negative voltage, if I apply a negative voltage, what happens? All the electrons will be repelled from the surface of the semiconductor to the bottom. Now all the minority carriers, holes, will be coming to the top of the semiconductor just beside the oxide layer. This is the oxide layer, right? So what happens? So net effect, what happens because of the electric field generated through the oxide, there is no current here, but electric field is very strong. So negative voltage attracts a lot of holes, so this positive carrier, now this junction or the channel is formed, complete channel is formed, resistance is reduced. So there is now, if I give a voltage, there is a current is passing and I get output voltage here, right? This is the controlling mechanism of, this is P MOSFET, P type MOSFET. So, so we have a negative voltage. Gate voltage is negative. You can see the gate voltage is negative in terms of P MOSFET. That means VGS is like this, whatever, or this can be zero, or this can be minus 2 volt, minus 3 volt, whatever. So reverse is the case of the n-channel MOSFET. We have P material, we dope using to n-type material, and we have an oxide, we have a metal. And now, if we applied a plus voltage or plus voltage VGS across gate, and this is source, so and drain, this is drain, we give a positive voltage for the current flow. Now what happens, because of the positive voltage, all the holes at the top will be repelled into the body of the semiconductor and the electrons. If we increase the gate voltage again and again, all the electrons, minority carriers starts attracted from the semiconductor material and start accumulating in the top layer. Now what happens? There is a layer formed of n materials or electrons. Now the electrons can easily flow and there will be current ID. Okay, so this is the mechanism of a, what type of an N channel MOSFET. This is the P channel MOSFET. Okay. Now, whenever try a new type of transistor, you have to think. Now we are talking about new type of transistor, JFET. So you have to think, what is the mechanism? What is the mechanism JFET is employing to control the charge flow? So that is the ultimate question you have to think. Okay, so JFET is nothing but junction field effect transistor. Junction field effect transistor. So there's a junction through which I'm controlling the junction. So while changing the junction, I'm changing the thickness of the junction. I'm changing the carrier flow or charge flow, right? So change it. So here also the question is how I'm going to control the junction. Okay, so JFET is like, it looks like very simple. So it's a PN junction only. So let's draw the JFET. Okay, so just like this. So yes, I'll take eventually I'll take a P-type material here. You can say I'm taking a P-type material, type semiconductor, right? So over this P-type material, I am doping the N-type material in this side and this side, right? So this, you should imagine this is a 3D structure. This is actually a 3D structure. Okay, 3D structure. So now what will happen? Now I'll just connect some voltage source to have. I need some current flow. Right now there is a current flow. I'm giving some voltage V, right? And maybe I have some resistance here and something I'm connecting. So now there is a current flow. There's a current flow because there's a lot of holes, and holes can definitely conduct the you know, the charge carry circuit. So this is R. So let's take initially N channel. So I'm just reversing. I'm just using the one more thing. Say I'll take another semiconductor. This time I take N-type semiconductor, right? So over this N-type semiconductor, I'll go to P-type layers. So what I'm doing is, it's like 3D structure. You should remember that I'm sandwiching N-type material over the P-type material, something like this. Initially the channel is N. So right now also is similar to the right structure. I have voltage here. There will be a current flow. I can have a current flow to the, because there is a lot of charge carriers to the N channel. So there will be a current flow even if the resistance are right. Now this is just a tank and the pipe. Now how is the control happening? Where is the control happening? Now, how the current is flowing? Now we can see there's a channel here. There's a channel. Where the channel is? This is the channel. This is the channel. This is the channel through which your current charge is going to pass. This is the line channel. This is electrons. A lot of electrons are the lot of electrons are in the channel. So I can easily pass the current. Here in p-type, a lot of holes are there. A lot of charge carriers are there in terms of holes. So holes is just opposite of electrons. So if you consider the current flow opposite, it's just flow charge. So here also there is holes can easily transfer the current. So there is can be current flow. So this is the channel, right? This is the channel. Channel. This is the channel. Channel is here also. Now, how am I going to control the channel? So controlling the channel, I'm going to control the current flow. The idea here is I'm going to give a bias in the PN junction. So here, what I'm going to do, if I need to control the current here, so both these connections are same. You should remember both these connections are same material. They are connected together, right? You should imagine like that. These are connected together for your convenience. I'm just trying to show you these are connected together, right? Because these are same MTI. This is 3D structure. That's your term. This 3D structure. Internally, these are connected. Both have will be connected. Okay, so 3D structure. Okay, don't need to do any confusion. This is only a PN junction analysis. Now what I'm going to do is I'm trying to control the current by changing the depletion region between the N and P type region. So we know in a PN junction, in order to increase the depletion region, I need to have a reverse bias. In order to increase the depletion region, I need to have reverse bias. That means P should be given to the minus and should be given to the plus. So this is the depletion region. So this is the depletion region. Depletion region, right? So here I'm trying to give a depletion region in these two cases. So in the first case, this is the first case, and this is first case. This is N channel. Second case is P channel. So N channel, how am I going to give a depletion region? So the P region should be connected to the reverse voltage. For example, this has to be given to be a reverse voltage minus, and N has to be given a positive voltage, right? So there is a connection in the N region also. So the N have to give a sorry. So N I have to give a positive voltage. For example, just showing N type metal I'm giving a positive voltage. Right? So what happens? Now you can see this region. You can see this region. This is P type. Here I'm giving positive plus. Right here P. I'm giving a negative here. I'm giving a negative. Right? Negative. If it is a bit confusing, I'll just you because of this side loop, I think it's confusing. So I'll just erase that thing. You don't need to worry about this leak. Okay. So here what I'm giving negative voltage to the P region. This negative voltage to the P region, okay, and positive voltage to N region. So here we can see there is here also is negative. I'm giving internally this is negative. So what happens? So this is a reverse bias happening here. This is plus, and this is minus. So both having because of this we'll get a form a depletion region because this point P and N region it's a depletion region, right? And this depletion region, right, will be devoid of charges. Will be devoid of charges. So you can see what happened. Net effect. What is happening? The channel is reduced. When the channel is reduced, you can see now less flow of current can happen to this channel. I. This is I. Okay, I channel I current. So what happened because of the negative biasing of P and N type material, my channel has been reduced because the depletion region has been increased. Now, if I increase the voltage, if I increase the negative voltage, what happened? This channel is going to reduce further because the depletion region is going to increase further. So current is going to reduce further, right? Again I increase the negative voltage. So again this is going to increase the channel reduce, channel is reducing again, current is becoming very less. Now again I increase the negative voltage, and at a particular point of negative voltage I can see the whole channel has been completely absorbed by the depletion region. Getting? Now there is no channel, this now current cannot flow, current becomes zero, there's no current flow. So this is called cut off condition. So this is called, point is called pinch off region. This point is called pinch off. You remember this term is very important. Pinch off. Pinch off. Channel has been completely off or pinched. Pinch off region. Pinch off region. So that voltage at which your pinch off happened, that is negative voltage. That means gate. So there is a voltage I'm applying here. So VG gate. This is the gate actually. This is the gate. This is one point of the gate. This is another point internally connected. The gate source voltage. So this point, we gate voltage or gate source voltage I'm applying is called pinch off voltage. Pinch off voltage. Pinch off voltage. Okay. Now same will come to the P channel JFET. So what about P channel? Right now there is a good current flow here. Current is easily passing through. Now what I'm taking the N region and I have to give a positive voltage for reverse bias, right? So in this two N region, I have to give a positive bias with respect to the P region. So I'll connect it to a battery source like this, plus and minus. Now this is also controlling voltage gate source. So this is a drain. This can be considered the drain point. This can be considered the source point, right? So similarly here also the N MOSFET also, this is a drain. This can be considered the source, right? Okay, so right, what happens because of the VGS positive reverse bias, the PN junction is now reverse bias. So reverse bias starts forming between P and N regions, right? So this is devoid of any charges. So the channel has been reduced from the initial value. The I is going to reduce. So I is slowly reducing. Okay, again I increase the VGS reverse bias. So again the channel is going to form more and more and more. Again the current is reduced further. Current is reduced because channel is reduced. So less carriers can flow. Again I increase the reverse bias. Again the channel is going more, depletion region is affecting my channel. Now particular negative voltage or reverse bias voltage or VGS, the whole channel is completely uh, absorbed or devoured by the depletion region. So the current becomes zero. Current becomes zero, and that point is called pinch off. Pinch off point. Pinch off, and that voltage is called pinch off voltage. That particular voltage at which my P channel has been completely absorbed by the depletion region, pinch off voltage. And you can see here the pinch off voltage is positive for a P channel. P channel. This is VGS is greater than zero, right? Here you can see greater than zero because gate voltage I'm giving plus, because N is here. I have to give a reverse bias in N, so I have to give a plus. So VGS greater than zero for P channel JFET. P channel JFET, right? So we have seen two types of JFET. What are the two types of JFET? One is N channel JFET, and there is P channel JFET, right? So basically, what is analogy? What is the analogy you can understand in order to understand the JFET? So it is like it's like we have a pipe. You can see. Okay, it's like we have pipe. So we have a hose pipe which you water the plants and all those things. So what happens, we have water flow here. Water will be completely easily or freely flowing whether it's a pipe connected to a tank or pipe. So what happens, the water will be completely or easily flowing through the pipe with force or something. Okay, so channel is completely formed and channel to the channel electrons. So what happens when we squeeze the pipe? We can squeeze the pipe at a point here. So when we squeeze using our hand, we can squeeze the pipe. So some pressure we can apply on the pipe. So what happens? The channel is going to reduce. The channel is going to reduce. So the current flow is going to reduce because the channel area is going to reduce. Right. So this is best example for the JFET. We are trying to reduce the channel or the flow of the water or current here. So the water flow will be reducing. So we can see, say, because of the some squeezing or pressuring or voltage applied, my current is going to reduce. Current is going to reduce, and becoming a zero at a particular point, right? So this is the basic principle of JFET. So how we are doing? We are giving a reverse bias using a reverse bias. So by reverse bias, we get a depletion region. So depletion region will happening or is produced in the channel. So channel will, some portion of the channel will be devoid of charge carriers. Okay. So this is the best example, water flow. Right. Squeezing the pipe, the channel is reduced and water flow is reduced. Ultimately, if we squeeze further, this will be no flow in water. So there will be voltage at the point where current will be zero. So that point is called pinch off, and that voltage at which this pinch off occurs called pinch off voltage, v pinch off, or we call vgs off, vgs off, because ultimately we are working on the gate source voltage. So that voltage vgs off we represent by pinch off voltage, vgs off. Okay, so this is basically back to the structure of JFET. You should understand that main point is in a N channel, the VGS is negative. In a P channel, VGS is positive. Now let's draw the um, curve if possible. So see what is happening with the current. Let's take an example of N channel JFET. Okay, so say this is VGS. So what happened? We are giving a reverse bias in the N trigger. So N channel, our semiconductor on the sides is P. So we are giving a negative voltage. So N channel we have to give a negative voltage. So initially when there is no voltage applied, so this is your structure. This is your structure. This is N channel. We have two P regions on either side. So initially the channel is well and good. So current can easily flow through this channel. So current is maximum without any voltage. Current is maximum. We can call ID saturation. You can say maximum current. This is ID sat. Okay. We have flowing through the MOSFET. Now, when we apply reverse bias, that is minus here, plus here. So this is, you can see VGS minus VGS. But now the depletion region is going to form. The depletion region is going to form here. So how the depletion region form? Here and here. So the channel is reduced. Ultimately, we need to pump some other current or using some voltage, VDS, drain source voltage. We have to pump current also. That is another thing, right? So that there is a current to the channel IDs. Now what happens? Now as I increase my as I increase my VGS to reverse negative voltage, you can see in a nonlinear way or in a quadratic way, the IDS ID is going to reduce. It is going to reduce something like this. In a particular point of VGS, my ID is completely zero. So this point is called pinch off voltage, VGS off, VGS off. Right? So this is such. So someone may ask, what happens if I increase the VGS in positive direction? No doubt. If you increase VGS in positive direction, maybe this may increase. This may increase, right? So this may increase, no doubt. Okay, but there is no control. We don't need to operate in plus VGS in N channel MOSFET because there is no control operations like just exponential increase in the current. We are not interested in that. We are interested in controlling. Transistor means controlling the switching or whatever. Okay, so this is VGS versus. So this curve is called transconductance curve. It's called transconductance curve. Transconductance. So in network theory, you might have learned resistance. Opposite of resistance is conductance. What is transconductance? Trans means always trans parameters, transformer, right? That means input-output relation between input and output. That is trans, right? For the transistor, this is we are controlling the output to the input. Ratio of the current is very high, so that we transistor. So trans means output and input. So here conductance means one by resistance, conductance. So we can have the ratio of transconductances is IDS divided by VGS. That means input. That is trans. Trans means output to the input. So based on the input, here input is the VGS, what the output? Output is the IDS current. So current to the voltage, that is the resistance, one by resistance. So that is conductance. It's not trans resistance, nahi hai, trans conductance. It is a trans conductance. So we have to take the dimensions of current divided by voltage. So we have I divided by VGS. And what about trans? Trans means relation between output and input. Okay, so this is called transconductance curve, which we have drawn here. Right, that just to understand the term. Transconductance usually represented by GM, transconductance. transconductance. Okay, so so okay, now if this is clear, now we'll go to the next curve. That is, now we have to draw the drain source characteristic, output character. This is input characteristics. Let's draw the output characteristics. So output characteristic, we are interested in VDS. VDS, how much I'm pumping the current and how much current is net affected. Okay, so VDS will get like usual thing. If it is zero, we'll not get any current, right? Because this is our structure, this is our channel. This is say XN channel. This is P. Now this is a VDS. VDS. Plus, I think VDS is zero. I'll not have any current. That you should know. Okay, so this is my VDS. Initially it is zero. Now, if I increase my VDS, if I increase my VDS, what happens? Definitely there will be current flow. So definitely there will be current flow. Now the pipe is now the pipe is on spotless point to the pipe. So initially it will be linear, right? Initially there's a lot of channel space areas there, so it will be linear. A particular point, we know the pipe capacity is saturated, so it will be saturated, right? If I increase, go on increase, it will be cut off or break down. So leave that portion right now. So this is my VDS characteristics. Now this is happening. Maybe for example, here we didn't apply any VGS, right? Here we didn't apply any VGS, so that is the case where we didn't apply any VGS. That means we didn't apply any reverse bias across this point, right? So I'll call this, I didn't apply any. VGS was zero. Now I'm going to start to apply some VGS. Now it applies a reverse bias, so this should be minus and this should be plus. Now I should increase. Initially I'm zero, I'm starting with some VGS. So this I call VGS equal to zero, right? So now I'm going to increase the VGS. So what happens? I'll get a new curve. Reverse. So what happens? Reverse by depletion vehicle is formed. So this is going to be reduce my current, something like this. Okay, now here the new VGS, I'll give VGS equal to minus 1 volt, right? So this is the new VGS. Okay, now again what I'll do, and I again increase my reverse voltage. I'm again increasing my reverse voltage. So again the new character, something like this. Say this is VGS equal to minus 2 volt, and go on like this. I'll get go on like this. Getting some curve here and there till a cutoff value. This is value VGS. So this VGS equal to minus 5 volts. So this is called pinch off. We already cut off a pinch off voltage. Pinch off voltage. There is no current here, right? So here also we can also plot the VGS in the left axis for comparison. For example, if I have VGS here, if I plot the VGS in the left, this is negative. Initially, we can say this is the saturation current. We can say this is the point where I don't have any VGS, so current is maximum. And now this is a point where I have a negative VGS is minus 1. So this is VGS minus 1. My current will be intersection of these 2 points. So this is my current here, right? Again, VGS is equal to minus 2. Again, minus 2. This is my minus 2 point, minus 2. So this is my current. Again, minus, again this continues like this. Again, minus till minus 5, I'll get something like this. So you can see this will not be linear, this will be a non-linear. This is VGS equal to minus 5, pinch off voltage. This will not be linear, this will be a curve only. But this will be IDSS. We call saturation called IDSS. IDS saturation, IDS saturation current. It's called IDSS. IDSS, represented by IDSS. Something like this, nothing but this. This is the IDSS. Okay, fine. So let's see. Let's try to make an equation of JFET. So mathematical. Now we know the working principle of JFET. And let's see how this mathematically we can have a model so that we can understand at any point what is the working of the JFET. And tomorrow morning we can have a test. I think 10 o'clock will be fine. Analog mock test. If you're ready, we can have a analog mock tomorrow morning. And if you're fine.
Yes, sir.
Okay.
Yes, sir.
Fine, fine. Okay, so we'll have tomorrow 10 o'clock. So I'll just put in the group so you can just brush up for the basics and we'll do it. Okay. So right now mathematics. So we are concerned about controlling the current. So in JFET ID, JFET current equation, you can write the JFET current equation, JFET current equation, JFET current equation ID. ID equal to IDSS. This is based on Malino. Malino also there is this 1 minus VG, gate source voltage, divided by VP, V pinch of voltage square. Okay, so here the main thing is VP. What is VP? It's nothing but V pinch of voltage, VGS off, VGS off, right? It's called V pinch of voltage, pinch of voltage. Okay, so this is a simple equation. Everything we know. This is this IDSS is the saturation current when the VGS is zero. The current when the VGS is zero. This is saturation current. IDS saturation current. VP is the pinch of voltage. VGS is the gate source voltage, and ID is the drain current. So, so what else is modern? Right. So this may be a constant. This may be a constant for a device. For a device, this may be constant. VP. You can see the data sheets. So that in this JFET, our VP should be this much. That means that voltage, our JFET is going to be completely cut off, or zero current is going to pass through the JFET. That is pinch of voltage. That's a constant. And other things we can vary. Means this is also constant, IDSS. And all the gates voltage is zero, IDSS is also maybe constant based on the VDS. We apply VDS. So here we assume VDS is constant, I think. So VDS is pushing or pumping some IDSS maximum current at that VGS. Right? We have seen this now. This is the graph. Again, for your convenience, this is the VDS, and we have some IDSS without any voltage. There is some IDSS. This is IDSS. IDSS means it is as VDS is increasing, IDSS is increasing coming saturation. This is IDSS, right? This is IDSS. So what about VGS? VGS is we are applying some gates was already. So maybe this is initially this is zero. Corresponding to IDSS, VGS should be zero only. Now we'll have a new curve something where VGS is different. VGS is equal to minus 2 volt here. So here this is not ID. This is ID. Now this is what the equation is giving you. ID. ID at VGS equal to minus. So we need to find the ID. So we substitute the value of VGS in this equation, VGS. And other VP is non, VP will be non, and IDS will be given to you, right? So basically, we are trying to find ID for a particular VGS. Other things remaining constant. Okay, at a particular VGS, what will be my ID in a particular device and channel or P channel, where this will be a somewhat constant, VP will also be a constant. So in a questions you may ask, given IDSS and VP, given VGS also find ID. So this is normal question using this equation. Okay, so other graph also should remember VGS is negative and this is N channel. Okay, this is VP pinch of voltage. This is IDSS, maximum possible current. So as VGS is negative, 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 and current is decreasing. Okay, so exactly opposite will happen in the P channel JFET. In P-channel JFET, we know VGS is going to be positive. VGS is going to be positive. So maximum IDSS will be here, and as my VGS is increasing, it will be going to decrease pinch of voltage. Right. So this is the transconductance. I repeat transconductance. So this is trans. Trans means output to input or input to output. Basically, it is output to input ratio. So this is output to input ratio. Then conductance. Conductance means one-way resistance. So this should be current. This should be voltage. So this is nothing but IDS divided by VGS. Transconductance. So this is nothing but GM. This is called GM. Transconductance. GM. Okay, although you don't need to go deeper about what is GM and all those things, this will be coming, I think, the coming semesters, as we are not have covered the basic electronics. So this is important. I think maybe we can do a problem. We can stand. We can stop. So maybe can. So yeah, we'll have some solid problem. I hope it is visible. This man we are taking from Malvino. So okay, I hope it's visible. Okay, so here's something. VGS off is given, pinch of voltage is given -4 volt, IDSS is given, IDSS is given as 5. Okay, so VGS off is -4, IDSS. What are the gate voltage and drain current at half cutoff point? So you know half cutoff point is, you should know, at the cutoff point is VGS, pinch of voltage. Pinch off is here, the pinch off, pinch off is nothing but -4 volt. That means at that point my current is going to die down. So I think we understood. This is the pinch off voltage. This is the pinch off voltage. So half cutoff point means half pinch off. That means this is the half cutoff point. This is -4. Half cutoff point means -4 divided by 2. Is -4 divided by 2, -2. So this is my half cutoff point. So by default, by asking the half cutoff point, I should know this is nothing but V pinch off divided by 2. It's also given. That is V pinch off voltage is given -4. This is -4 divided by 2. That is -2. That is also given. So we have the drain current equation. So let's draw the drain current equation. Based on that, we'll try to solve this problem. IDSS 1 minus VGS divided by VP square. Right? So IDSS is given 5 milliampere, 5 milli, 1 minus VGS by VP. This is nothing but, we know VGS is -2 and VP is -4 and square. So this becomes how much? This becomes 5 milli into 1 minus 1 by 2 whole square. 1 minus 1 by 2 whole square. So this is 5 milli into 1 minus 1 by 2 whole square is 1 by 2 whole square. This is 1 by 4. So it's nothing but 1.25 milliampere. Okay, it's direct. There's nothing but direct answer. So we have another. So here, this is another MOSFET. Sorry, N channel. N channel. How you understand N channel? Because you can see this is negative voltage. VGS of is negative voltage. So we can understand this N channel. What is the question? IDS is given. What is the drain current at the half cutoff point? Same thing. Half means -4, right? So this is ID. ID equal to VT, IDSS, that is 16 milli. In the half cutoff point, definitely the same thing will apply here also. It is 16 milli into 1 by 4, about 4 milliampere. So you can see the biasing. Here also the biasing will apply. Based on this biasing, we can see the different values of IDSS, different curves are coming, right? Right. So this is also a biasing point of view you can discuss, but this is beyond the topic. We don't need to discuss so much of this. So again, load line. We are drawing the load line. This is the output Kara. This is the load line. Load line. Over the load line, I'll plot the device characteristic, device scanner. So I'll call the Q point. This is my Q point. So this is the operating conditions. ID versus VDS. This is ID. This is VDS. So this is the operating point. Operating point. Again, this everything is. I think the VP is given, VGS of is given, and before point A in time, the input is minus 10. The input is cut off. In this case, drain voltages. I think based on this thing is given. Figure it is given. Okay, so you have to study that equation, and other things, voltage divider biasing and all those things will be similar, but you don't need to go deeper on to the biasing of JFET and all those things. Okay, so I think we'll stop it here. Any doubts we'll discuss, else you can put your roll number. And tomorrow 10 o'clock morning, I think I will share the link in the Google Classroom. You can go through, you can see the analog circuits here to brush up the diode. Basically I'm putting the questions from diode only, diode. So you can brush up the diode also, and you can. I'm putting some questions. It's not about getting marks. You should need to practice. That's it. Some putting some gate kind of questions for your. Although we have discussed, we'll discuss, but it'll be good. Be good for you. Fine.